You can think of it as like a bank account. There are systems where you can pump a lot of water out of the ground, but there's also a lot that goes in from the rainfall or coming in from rivers or lakes. And that can be fine. But there are ways to capture water on the surface and just give it a little bit more time to infiltrate. Then you can end up getting more water into the ground. But you need to be careful about quality issues with that, because if you pump a ton of not really clean water directly into your groundwater, then you can have groundwater contamination issues, which are very challenging to solve. There are huge energy and economic impacts. And then, of course, there's the point where the water passes some threshold where it just doesn't make sense or it's not possible to access it anymore.
Welcome to Liquid Assets. I'm your host, Ravi Karani. Liquid Assets is a podcast where we talk about the intersection of business, policy, and technology, all as it looks at water.
Hi, my name is Tess Russo. I am a senior program officer at the Bill and Melinda Gates Foundation on our agricultural development team. And I work on our climate adaptive systems and agricultural water management portfolio.
And Tess, without further ado, I'm just going to go ahead and hand you the mic. If you can kind of introduce yourself, tell us about where you're at right now, what you're up to.
Yeah, sure. Hi, thanks again for having me, Ravi. I'm at the Gates Foundation. I'm a senior program officer on our agricultural development team. My background, though, is in hydrology. I have a PhD in hydrology from an earth science department at UC Santa Cruz, and have done most of my work since then through my postdoc and onward in agricultural water management. So that's sort of why I landed on our agricultural team. And I can talk a little bit more about what we're doing at the foundation around water. I also spent a couple of years at a small invention company. Before the foundation, I was a professor at Penn State for a couple of years and then moved to this invention company where we had some programming around product development for irrigation in Sub-Saharan Africa and South and Southeast Asia. So aiming to support smallholder farmers, small-scale producers with irrigation and water access equipment.
Got it. Cool. Let's go ahead and unpack that a little bit. So the first thing I want to kind of touch on is your background in hydrology, right? So for the people out there that don't know what hydrology is, can you give us kind of a layperson's definition of what exactly is hydrology?
Yeah, sure. Sorry. I should, we have a problem at the Gates Foundation of using too many acronyms. And so I also need to now be careful about which words I'm using. Hydrology is basically just water science. So the study of water. And what I did in hydrology was looking at the hydrologic system and the way that humans and climate change are impacting that hydrologic system. So how water is moving through that water cycle. So like one example that we looked at was uh, downstream of a reservoir that was used for providing water to the city of San Francisco. They were doing some controlled flooding experiments. And so we were looking at ways to optimize the release of water so that it would have the greatest environmental benefits, the ecosystem benefits, but use the least amount of water so that we weren't, losing too much water for the city, but having these other benefits. So it's a lot of field work and numerical modeling, hydrologic modeling, statistical modeling, um, and depending on what side of hydrology you're on, you may do more chemistry, or you may not. So kind of can touch all of those areas.
Yeah, and I remember when we kind of had our first intro call, you had really talked about combining, and what you really loved about this is combining the physics, combining chemistry, combining numerical modeling. Feel like you're able to kind of put this full stack approach using hydrology actually out in the field. Can you kind of two things? One, can you like zoom out really quick? And you obviously focused on the hydrology being the study of water, focusing kind of on the hydroelectric system and how that kind of works. But like what other verticals in hydrology are there? And then secondarily, kind of, can you guide us through the field work that you've done? Because I think that's super cool work that you've actually done in your career.
Yeah, yeah. So, um, within hydrology, there may be a sort of taxonomy or typology of groups, but I would group it into sort of three main areas to begin with. One being surface water, so water that you see in lakes and rivers, water that we're storing above ground, groundwater. So then everything that's underground, all the water that we don't see, that when you drill a well, you access, or if you dig a pit deep enough, you might hit groundwater. So those are two, and then there's certainly the interaction between those two is a very active area in hydrology. So how you get water from the surface down into that groundwater system, and then how it comes back out in certain places. And then the sort of atmospheric water, which falls more into atmospheric sciences, I would say, but there are a lot of hydrologists who study precipitation patterns and the connection between that and the rest of the hydrologic system. So sort of things that are happening in the air, things on the land, and then things underground, I would say.
Got it.
And
That's such a beautiful explanation. Yeah. Sorry, go ahead.
no, just trying to make it, simple, sort of something that you could imagine or see. I think groundwater being the trickiest of those three for most people to like really wrap their head around, what that is. And I think, I taught one of my classes at Penn State that I taught was a introduction to hydrology course, and we talked about groundwater. And most of the students, when you ask, what is groundwater? What's groundwater look like? They think it's this a big underground lake, or something where if you burrowed down into the ground, you could like go swimming in it or scuba diving. And that's not what most of groundwater is. Most of groundwater is just packed in between the sand grains or soil grains or whatever the rock is that it's in. And it's not something you could, swim around in or have a fish swimming around in. There are some caves, that are part of the groundwater system where there are larger bodies, but it's it's somewhat harder to visualize true groundwater.
Yeah. Yeah,
So
totally.
yeah.
That's such an amazing explanation of hydrology. I think that would actually work work amazingly well. When we kind of now zoom into your field work, two kind of things I want to touch on. One is your field work that you did at the Columbia University Water Center in Punjab. And then the secondarily is, let's like go ahead and double click into this work that you did for San Francisco as well. I think it's really interesting for the folks out there that are looking to get into water to see the kind of breadth and depth of what they're able to do and what they're able to touch.
Yeah, yeah, definitely. So I have done field work and water related studies and science on 5 continents, um, right now. So I have done work in a lot of different environments. Most of them have been tropical or, warm areas. So I don't do work in the poles. Um, but where great glacial hydrology or oat fields might be, another interesting area that I won't be able to talk about. But my work in India and in Punjab, um, was focused around, water availability for agricultural users. And Punjab is a really important state agriculturally within India. It produces a kind of outsized percentage of the rice and wheat that is consumed internally to India. And there's a fair amount of exports as well on the rice side that come out of Punjab. And so, when there were great strides made in the 70s, 80s, 90s in India in terms of just domestic food security, and in large part that was due to increased intensification and food production in Punjab and neighboring states, as well as across the rest of India for other crop types. However, and this was great, they did an excellent job producing more food. Um, but it was somewhat at the expense of the water resource availability. So what we're seeing, for example, in Punjab, they most of the water is coming from groundwater. So they're pumping water out of the ground to irrigate rice and wheat. And what we're seeing when we look at the groundwater condition or how deep you would have to drill to find that water, that depth is going down and down and down and down. It's just like if you had a cup and a straw and you were drinking the water out of the cup, that level is going to go down and down and down in your cup. So it's essentially the same thing. It's just happening in a big rock formation underground. And so, and that happens when you don't have as much water going into the system as you're taking out. So you can think of it as like a bank account. There are systems where you can pump a lot of water out of the ground, but there's also a lot that goes in from the rainfall or coming in from rivers or lakes. And that can be fine. So that's what we call renewable groundwater, where the system is kind of in balance with how much comes in and goes out. And what we were seeing in parts of Punjab, most of Punjab actually, is it was farmers were accessing what we would call non-renewable groundwater. It was groundwater that had been there for a very long time, and when they pull it out, there's not enough going in, so we're seeing that decline, which has impacts in on a number of things. One of them just being the ability, the cost of getting water out is going up, so you have to use more energy to pump water further up, and you need different technologies. So you need a different kind of pump depending on, the depth of the groundwater. There are a couple of thresholds where the technology has to change, and that means farmers have to go buy a whole new set of technology. So there are huge energy and economic impacts, and then, of course, there's the point where the water passes some threshold where it just doesn't make sense or it's not possible to access it anymore. And then what do you do? Then you've got land that you can't irrigate, and maybe you could grow something during the rainy season, the monsoon season. But it's a real challenge, and it's a real challenge for the farmers themselves and for the politicians in the area to develop a solution that would have the support of all of the farmers. So this is an ongoing issue in Punjab.
Yeah, especially kind of from what you were saying of Punjab being one of the largest providers of food for the country, and having that issue of your largest input being this kind of runaway resource, it's really probably hard to maintain that output of continually maintaining food. Um, One thing that kind of hit me is when you talk about this bank account, right? You have a budget and your groundwater, you have your revenues coming in, right? You have your costs going out. And if your margin in between dwindles, you're gonna end up being in the negative, right? Which ends up being a problem for the entire budget. Um, you said there's the renewable groundwater system, in which case your revenues and your costs are equal, so you're keeping a pretty static margin, or you're probably increasing in that sense from a supply standpoint. Is there ways outside of just not pulling that much water out to actually turn a groundwater system renewable? Like, is there a way of putting more water back inside, or is it just kind of a lost cause and you need to go back to the drawing board to figure out where you can grow food otherwise?
Yeah, that's a great question. So just like of any bank account, you can look at what can I do on the demand side or the supply side? Can I withdraw less money? Can I earn more money to put into my bank account? Like those are the two sides. And so there's certainly demand side things that can be done. Growing a crop that uses less water, changing the irrigation method. So instead of a flood irrigation, using something like a sprinkler or drip, um, which has issues in itself, but we won't go there. And then on the supply side, yeah, there are things you can do. So if you think about the way groundwater recharge works, is the water falls as rain primarily, and it has to seep into the soil and go all the way down into the groundwater, and that takes time. And the soil can only take so much water at a certain amount of time. And so if that soil is at capacity, like if you have a heavy rainfall, you might see water just running off over the surface down into rivers or lakes and then out to the ocean. And so if there are ways to capture water on the surface and just give it a little bit more time to infiltrate, then you can end up getting more water into the ground. And that's there's something called managed aquifer recharge, where the aquifer is the word that we use for describing the groundwater systems. Um, and so managing that recharge allows us to increase the amount of water going in back into the groundwater. And that can be done through like large, essentially just building a depression, in the ground that you funnel water into and then just let it sit until it seeps into the ground. It can be a very low tech solution. Or you can capture water and then pump it into the ground. And there are pros and cons to both of these, obviously. There's actually a lot of examples of this in California, um, of managed aquifer recharge in practice. And I would say the pumping it into the ground is may sound like, well, that obviously is the best solution, especially if you already have all these pumps. But you need to be careful about quality issues with that because if you pump a ton of not really clean water directly into your groundwater, then you can have groundwater contamination issues, which are very challenging to solve. So, so quality is a
Which
is a
which is
concern.
kind of which is really interesting that you said, the your students would primarily think that groundwater is this, large pool of water that's just underneath the ground, but it's the opposite of that, right? These water molecules are stuck in between really small grains of sand and in the different strata of the ground. If you have a contamination event, it's not like you're going to a pool underwater and just draining that water out and refilling it back up. I mean, this stuff is has a density to it, and it's probably in a particular area, and it's really hard to take that out or fix it, right? Or what kind of our plans are? What you just raised this question in my mind of what happens when you contaminate the groundwater.
Yeah, it is tricky. It's a sticky problem because you can have some contaminants, as you said, that are different densities. So you might have like thinking about oil and water, how they don't really mix very well. So if you had a oil leak or something into a groundwater system, it would do the same thing. It would stay kind of separate, which is sometimes helpful because then you can remediate just where the contaminant is. But sometimes it's trickier. The main approach to it is you build a loop of either pumping in clean water and then pumping out the dirty water and then treating it. So it is kind of like emptying the pool and in a way where
Yeah,
you then
yeah.
treat that water, but it's just groundwater. But yeah, the sort of pump and treat is one approach. But it can be hard because as you said, there are all these little crevices between the grains, or there might be tiny cracks that the contaminant and water um is in, and it's really hard to like fully clean those. And so you can end up with like vestigial, little bits, residual contaminants that last a very long time in the system.
Yeah. And which actually raises another question around sensing, right? You have this balance sheet, this budget. If the water is not contained in a pool, you can't just stick one sensor inside there and understand what the actual quality or quantity of that pool is. What does sensors and technology look like to make sure that you're not over pulling your budget
Yeah. So um for groundwater specifically, yeah.
for groundwater? Yeah.
Yeah. Okay. So generally what we do is within a given aquifer or groundwater system, someone would usually go in and drill a number of wells, monitoring wells or exploration wells, where they're getting an understanding of what all the different rocks are that are making up this aquifer, what layers exist. And then you can start to understand how connected the whole system is. Because you could have something like, let's say, a really great layer of sandstone. It's got a bunch of good water. You've measured it. It's good quality water. And then you have a clay layer under it that's really going to act like a barrier. And then underneath that there, let's say there's another sandstone layer that also is a good aquifer. Those two aquifers that have the clay layer between them may not be sharing any water with each other. And so if you have one well that goes all the way down into that lower aquifer and one in the top aquifer, they could be reporting completely different levels as each other because they're not sharing water. But if you have two wells or two straws, like, in a bowl, they're both gonna show water at the same level. And so as long as you're connected in that connected aquifer, you're really just measuring the height of the water. So it's what we
Sure.
call the head,
Yeah. Right.
in that upper aquifer. And in the lower aquifer, we're also measuring the head, but it's under pressure, so it's like a pressurized head. Um, and so, yeah, so the sensors that we use for that, there are it's pretty simple to deploy. They tend to look, um, I don't know, about the size of a carrot, I'll say. Um,
Mhm.
and they're for measuring pressure, and you can program them ahead of time. The sort of simple models that will monitor or measure pressure every however much time, however often you want, every hour, every day. Um, and you can have some of those systems connected into telemetry, and so they're reporting out information so you can get it semi real time. But that's a relatively easy measurement to make. The sensors cost on the order from a couple $100 to a couple thousand, depending on the type of system. But you really do wanna have multiple of them because of that connection issue where you're not exactly sure necessarily where you're putting the sensors, and because the groundwater is moving, right? Which is the other thing we haven't talked about, but there's a natural flow to groundwater, and when you have multiple sensors within an aquifer, you can tell the direction of the flow. And that tells you something about maybe where the water is coming in or leaving, or if you had a contaminant issue, where you would want to, move to, either to avoid it or to treat it. So yeah, so it's something where you typically want to have, I mean, as every scientist will say, more data, more sensing points. But
Sure.
the yeah, pressure is an easier one. The measuring water chemistry is a lot trickier. Um,
And how is since you just opened up that I was gonna run to another question, but actually,
oh,
how do you measure water chemistry and why is it tricky?
well, so one of the challenges is, especially in depending on the environment that you're in, agricultural or industrial area, you may not necessarily know all the potential contaminants that you need to measure.
Mhm.
And so it's relatively easy if you say, all I need to know is, nitrate concentration and, something, something, something. If you know what you want to measure, you can go and take samples and make those measurements, or put something in situ into the system to monitor water quality. Those are somewhat newer, um, over the last decade or so, and certainly more expensive than the pressure measurements. But again, there might be something else added into the water that if you don't know you're supposed to be measuring for it, it's probably not being measured.
Yeah, 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 completely makes sense. I wanna switch gears a little bit and jump to your experience and your work at the Gates Foundation. I remember when we were talking previously, you had kind of moved around a little bit at the Gates Foundation. Can you kind of walk us through the storyline of Tess and Gates?
Yeah, sure. Should I go back to the Gates Invention Company or just stay at the foundation?
Yeah, no, I think that's a really cool through line, definitely.
Okay. Great. So I started at a company called Global Good that was a sort of joint venture co-owned by Mr. Gates. And we had two primary teams, one in health and one in agriculture. And we were a product development company for primarily serving clients in sub-Saharan Africa and South and Southeast Asia. And I worked on our irrigation products as well as some of the soil diagnostics projects. So measuring how much fertilizer is in the soil in a very low cost, simple way. So that was a big part of what we did was taking technologies that either already have been invented and are in use in the global north, but are not yet affordable or not appropriate for the environment or the use case in Africa, let's say, and working on that development. And so identifying, what needs to be done differently, and then working with a manufacturer who would then take that design and own it, take it forward, and provide it to the team I was on, the ag team, so the farmers of interest. And so I moved from there. Oh, sorry, go ahead.
I was gonna ask what happened next.
So I moved from our agriculture team at the invention company over to the agricultural team at the Gates Foundation. And I started on our strategy team. And part of the reason for me joining that team was because we were developing or exploring what we should be doing in the area of climate adaptation on the ag team. So trying to think about how is climate impacting what we're trying to do on agriculture, the goals that we've set, and if we were to refocus in some way or identify key areas to work in, what would they be? So where do we need to put more effort or more concerted focus? And part of that was water. So we needed to start paying a little bit more attention to water and the water space. Yeah, so I joined the agricultural team because we were starting to look at and explore the ways that climate was affecting our existing goals and the work that we were trying to do on the team. Um, and a big part of that was looking at where we needed to potentially double down and do more work and more focus, and where we needed to move into potentially new areas. And so part of that was the area of water. And we recognized that so much of climate change, especially for agricultural users, it kind of manifests as changes in water availability. So, for example, a period of drought or a flood, these are going to have major impacts on agricultural productivity, and they're really just changes in the water cycle. And so we started, kind of went back into the work that we had done in water and looked at what we had learned previously around irrigation primarily, and then have come out and developed a kind of new approach, a new strategy to approaching water on our agriculture team.
And what exactly is that kind of new vision or new way of looking at water now on the agriculture team?
Yeah, so I won't say it's new. It's not something that is new to the general community, but it's new to us. And what we're doing is we're taking a higher level approach rather than just trying to get irrigation systems out to small scale producers or farmers. We're instead looking at how is water being managed? What is the relationship between decisions that are made that are impacting water in agriculture versus energy versus the environment? And so the whole approach is called Integrated Water Resources Management, IWRM, which is a uh, well known, well understood approach. But I'd say that's the framework that we're using. So a big part of what we're doing is working with in the countries that we're serving. So again, primarily in sub-Saharan Africa and South Asia, to help to better understand what decisions need to be made around water management, and then what are the data and analytics or decision-making tools that are needed to make those decisions. And a big piece of this is recognizing that it's not just one time that these decisions need to be made. It's not something where we can, bring in technical experts and say, okay, here is the best way to manage water, in your context. Because of climate change and human development, we've got changes to both the supply and the demand side, and that changes, with space. So it really needs to be something where a a country or a state or a watershed has the capacity to rerun that analysis and monitor how they're doing, assess how it's going, and um, adjust and decide what they need to do potentially better or differently. So
And so
it's the
tactically,
focus we're
when
taking
you're,
is, oh, sorry.
I was gonna say, and tactically, when you're kind of sitting with with a government or building out a policy that's going to be continuously iterated upon, um, what does that kind of look like in practice? Like, do you have an example of like a country that you've worked with or a particular jurisdiction that you've actually implemented something like this with?
So it's a new program, so I don't have any great successes yet, but I can tell you what we're doing in Ethiopia is
Yeah.
starting by having some conversations about what um, who needs to be in the conversation. So which ministries need to be
Mm,
involved. Um, Ministry of Agriculture, Ministry of Water and Energy, Ministry of Irrigation, Ministry of Environment. All of these different ministries have a stake in water decisions, and they may not be working together on how they're making those decisions. They may be not using the same data. They may have different models, and so they're all potentially coming to different conclusions. And so part of what we're trying to do now is think about, is there some kind of efficiency or some way that we could look at or encourage a sharing of data and analytical resources across these ministries or decision makers. So really bringing together like a water team that has
right.
representatives from multiple sectors, and standardizing some of the decision making.
Really cool. And when you kind of first approach the problem statement, do you initially come at it with a sort of matrix of here's the industries or the particular jurisdictions or the particular people that might be responsible that use the most amount of water, like let's say agriculture, for example, in the Punjab region, right? Just because we talked about that. If that's the largest user of water, do you then go to like the agriculture minister and say, hey, look, groundwater is a problem here, and these are the metrics in which we're going to lay out that's going to be a 6-month plan or a 1-year plan, and then we're going to revisit this again. Like, how does that kind of work out? What is that initial problem state, or are you guys finding that information to approach it?
Yeah, so I would say, some of it is awareness of the problem from our perspective, but that's also not something that's going to lead to long-term or lasting change. It really needs to be demand driven and, locally owned, locally driven. And so we may have some questions and observations based on, let's see, those declining groundwater levels in Punjab. But what we would do, and like what we did in Ethiopia, was we said, we think these are the main players. Let's go in, put them in a room together and ask, what are you doing? What are you working on? How are you approaching these problems now? Who are you engaging with? Who else should be in this conversation? These are all the kind of beginning exploratory questions that we ask, and I
Yeah,
think
yeah, got
the
it.
we
Um,
may have like a rough vision. Yeah.
yeah, yeah, it totally makes sense, right? You can approach the problem from both sides, where you may have an initial idea of what you think the problem is, but obviously taking in their feedback of the feet on the ground makes a whole world's worth of difference of actually understanding what they're really going through. entirely. I want to take a quick left turn, Tess, and kind of double click into into the world of Tess. What drove you to this? If you were to kind of look back, hindsight 2020, what's the through line of how, you it's so interesting when I speak to folks like you. They're like, oh, my dad did this in when I was growing up, or my mom did this, or I was just really interested. I played with XYZ toys. Like, is there any particular thing that if you go back to that through line of what really drove you to being the Tess that you are today at the Gates Foundation and working in water?
That is a tough question. I think that, I mean, I've always been really motivated by problem solving and, puzzle solving. And so I think, I did a lot of work in math and science and, through my educational career. I studied mechanical engineering as an undergrad and really enjoyed, again, the multidisciplinariness of mechanical engineering, where you have physics and chemistry and electrical engineering and computer engineering kind of all coming together. Um, so the variety was key to me. But I knew I wanted to do something that had kind of immediate and lasting impact um, in communities that had been more marginalized. And so I think that was sort of what moved me towards work in low income countries and developing regions. Um, and water is such a fundamental aspect of development in terms of agriculture, in terms of health. And so I think I knew water was going to be important. I mean, this was, I think, around the time when we were starting to hear things like the next wars are going to be fought over water instead of oil, or but that was kind of a new concept, which I'm sure someone listening will say, no, we've been saying that since the know, millennia ago. But for me, it felt like, oh gosh, yeah, well, maybe I could do something in that area. Um, so that was, yeah, that was it. I wanted to do something that I felt could be useful, um, and also kind of satisfied a intellectual curiosity, across a number of fields and disciplines.
Yeah, yeah, super inspiring. I ask everybody the same question at the end, which is there a book, a TV show, or like a movie or something that has really impacted the way that you view the world, or potentially in water? It doesn't have to be water related, but something that just kind of changed your worldview.
Gosh. I think, I mean, and someone may have already said this on your podcast, but for water, I would see Cadillac Desert. And maybe it was because I, read that during graduate school, but
Mhm.
um, it really does a wonderful job explaining the water management in the West and in the U.S. and how we kind of engineered and our way around that and the political side. And so it brings a lot together and makes it real because it's a, real case as well. So I think that one was pretty instrumental for me in terms of understanding the the scope of what, hydrology could impact and could do.
Got it. Interesting. Cadillac Desert. Yeah, actually, you're the first person to say that so far. Um, Awesome, Tess. Well, thank you so much for coming on the pod. We'll definitely have to revisit when you start deploying the strategy into more countries. I think it'd be awesome to do like a check in the next year or so to see how you guys have come along. Thanks again for coming on Liquid Assets.
Yeah, thanks for having me. Thanks, Robbie.
And for all of those of you out there, if you want to listen to Liquid Assets, you can find us at liquidassets.cc or anywhere else you get your podcasts or on YouTube today.